Hello everyone, welcome to week 3 of System and Skill Summer Edition. I'm Yun, the host of the conference. Last week, we talked about resource management problems. This week, we will focus on another type of a foundational service, storage and data processing systems. Interestingly, we'll hear about two different systems from different sides of Alibaba today. Key value has become a very popular solution to scale out storages. They are not only used by user-facing application directly, but also being leveraged by other systems as a building block for things like metadata management or indexes. Our first speaker today is Nathan Pang from Alibaba. He will talk about ArkDB, a storage engine built for Alibaba Cloud storage services. Let's welcome Nathan.
Hello everyone, my name is Nathan. I work in Alibaba's cloud storage team in Seattle. Though I'm making this recording from Philadelphia, I enjoy some family time and my daughter's drawing. So let's jump back to the presentation. First, really appreciate Facebook for this great opportunity to present our work. Here I'm giving you an introduction of ArkDB, a new key value engine we designed for our cloud storage services. My colleagues who have been working on this project are Qingda, Shuo, Ray, Yikang, and Jason. Before everything, let's talk briefly about who we are, or more precisely, in Alibaba, what we do. The company was founded in 1999, where it offered an online B2B marketplace. Then, in the next following years, Alibaba extended its service to B2C, C2C areas, as well as providing the electronic payment infrastructure, which nowadays plays a significant role in people's life in China. Alibaba entered the world of public cloud services in 2009, that is 3 years after Amazon made its move to establish AWS. Today's Alibaba is much more than just e-commerce and retail. It has great, and some are very good, impacts on people's lives in China and many other parts of the world. For example, we have services such as Cainiao, it's a logistic network. We have Youku, a video hosting service very similar to YouTube. Yale.me, that is an online food delivering platform, and many, many more. Now, back to what we do, the cloud services. You can see this is a big cloud provider with a large user base. Alibaba Cloud sees a huge development in the past decade. It is actually the #1 cloud service provider in both China and Asia Pacific. And if you consider the IaaS market share, it ranked the 3rd, right after AWS and Azure. Here are some products and services available today. There's a little bit too many to show in this small picture, but IaaS, storage, artificial intelligence, etc. Many of our clients are still in China, but we are also serving globally. We operate 74 availability zones in 24 regions. The team I'm in focuses on building cloud storage services that serve both our public cloud customers and our internal products, such as e-commerce. On this slide, we're showing 3 services that are representative of our cloud storage products. We have OSS, the object storage. We have NAS, and the table store, which is the NoSQL database. They all share a very similar architecture of 3 layers, with the top layer is the front end that handles user protocols and interacts with the clients. The middle layer manages the metadata and the runtime states. And the bottom layer is the distributed file system. We call that Pangu. It is the basis of all our storage services. The distributed file system provides the storage disaggregation with an append-only interface. Data redundancy is achieved with multiple replicas or error coding. We only support append writes for efficiency with modern SSDs. At the core of each service, you can see there is a distributed key value store. For example, in OSS, information such as namespace and the object data layout will be stored in distributed nodes. High scalability is achieved by dynamically splitting the data space into partitions and providing read-only replicas. Fast partition recovery and failover guarantees the high availability. So what is a key value store? Basically, it's designed to store, retrieve, and manage associated arrays. One example shown here is the metadata for a very simple object store, where two tables are involved. The first one describes the namespace and the metadata for objects, and the second one tells where to find the data for the object. A key value store needs to support operations such as put and get, while there's another important function which is range query. It's very useful that, for example, we want to list all the objects within the bucket or all the data segments of an object. A typical data structure to implement the key value store on persistent storage is B+ tree. We can easily see that updates must be propagated to the root page, which involves multiple IOs. So the actual implementation in the real world are usually much more complicated. Famous implementations include LevelGB from Google, ArkDB, that is actually from Facebook, and HBase. Modern key value stores we just mentioned are all based on log structure merge tree, aka the LSM tree. LSM tree is essentially a general design that organizes the data into multiple levels, where each level optimized for its underlying medium. The new data changes are buffered in the main memory, and once it reaches a threshold, it will be written to the storage sequentially as a new index file, while the new data can continue to accumulate in memory. To create the LSM tree, the in-memory index and those unstored indexes will be created, and the results will be merged in the end. For a good read performance, we have to reduce the number of index files by merging them. This is a process we call compaction. The compaction can result in significant write amplification. That is, the data written to the storage device is actually many times more than the data written to the key value store. On the right side, we show a widely used index file organization and the general idea of compaction. Other than level 1, the level 1 where different files are actually from checkpoints and they have overlapping key ranges. But other than that, each level has a list of index files with non-overlapping key ranges. Compaction reads the data from a level and find those files with overlapping key ranges in the next level, merge them, then write the result files to the next level. Since the next level usually has more data than the current level, say 10 times, the write amplification is introduced by this compaction task alone. There has been lots of work trying to reduce the write amplification introduced here. From our experience of running the cloud storage services, we observe that the following workload characteristics. A lot of our user workloads are write heavy. In fact, some of our clusters are dominated by ingestion loads. The write loads are then typically dominated by long sequential writes or repeated updates in a small key range, relatively a small key range. Many sequential workloads are from tasks such as backup or event logging, where the random yet hot writes are common for example, NAS file updates. We also observed a large number of range query loads, either from file or object listing or NoSQL range queries. Recent hardware advances really offer many opportunities for key value store designs. One big change is that the NVMe SSDs, they are widely deployed, offering much better bandwidth and latencies than those like SATA HDDs and SSDs. In particular, we have much better random read performance. Also, our regular server systems now have over 100 logical processors, 1 terabyte DRAM, and high-speed networking with RDMA support. All these above advances ask us to rethink the key value store designed to maximum their potentials. Our current storage services, like today, are built on a LSM tree based design that is over 10 years old. On one hand, is very robust. On the other hand, we have seen a few issues with this implementation. The conventional LSM tree design introduces quite large write amplification. The bursty compaction traffic often causes pressure on the CPU and I/O and make performance fluctuate. The original design had this SATA SSDs, small network and low CPU count on mind, and thus is not always suitable for our current hardware environment. And we have had to introduce quite some optimizations along the way. So we also have this recently implemented a completely new underlying distributed file system. We call that Pangu 2, the next version, to better utilize the modern hardware. So we have to take another hard look at our current implementation and think what we should do to modernize our key value store. The answer is this new design. We call that ArkDB. With the previously mentioned challenges and opportunities in mind, we try to overcome the shortcomings of our existing implementation. The key idea of this new design is to combine those from both LSM tree and recent B tree based designs like BW tree or B epsilon tree. This figure shows the basic idea of a BW tree. It buffers recent changes and chains those changes to the corresponding B tree nodes. Writes are localized without propagating all the way to the root page. It is optimized for the writes and the cost, of course, of a page mapping table, which maps the logical page ID to its physical address. With care, though, such a base design is also suited for our range query heavy workloads, since those contiguous key space are not scattered across several files. The page level compaction associated with such a design also reduces write amplification, since a lot of our write-heavy workload exhibits strong temporal and spatial data locality at page level. As we localize compaction at page level, small compaction tasks driven by frequent page access are less spiky, and they tend to interfere less with our user requests. Besides, NVMe SSDs, low latency networking, and large page cache also work well with such designs because the small arrays associated with having small delta pages are now just less an issue. A lot of our effort is centered around how we can design a highly scalable and available distributed key value store based on such basic design ideas. So this is the basic architecture of our system. We are still fundamentally a two-level SM tree. The first level is the memory buffer that are based on sorted index structure. And the second level is our storage level. We call that file table. A file table can be viewed as a BW tree with very different design, though, from the original paper from Microsoft. In particular, this mapping table, we're going to discuss that later. Same as the conventional SM tree design, the memory buffer is checkpointed into the file table when its size reaches a certain threshold. The file table persists its state, including page mappings on Pangu 2, the new distributed file system. Data is organized as several streams, and each stream consists of a list of extents. We always use this extent ID and its internal offset to describe the data location. Now we can dive into some details. Due to the time limitations, we not be able to talk about every aspect. So here are three important and complicated areas: page mapping mechanism, garbage collection, and how to support scale out. So basically the partitions. The page mapping, it allows page updates happen in the tree without propagating all the way to the root page. To allow this local update, we support two types of operations on a mapping entry. The first one is to append a delta mapping to the page. You can see from the first figure. Second one is to compact existing mappings. In this case, the delta 1 and 2 are merged into a new page, which replaces these two mappings in the chain. As we said, page mapping in ArkDB, they look quite similar, but it's actually very different from the BW tree design. We use the stream position as the page ID, so identity mappings, those pages without any deltas, are implicit. We don't have to store those in the mapping table. This allows us to shrink the table when it's necessary. The mapping updates are persisted in log and checkpointed regularly, so the whole mapping table can be recovered during a system failure. Each mapping also includes a timestamp to provide the snapshot isolation. For example, a get operation with the rate timestamp 2, we'll only be able to read those less than or equal to 2. Here you can see RCU-like mechanism is used for efficient concurrent access. In our design, page mapping related operations can happen concurrently, each based on its own view of the tree. It will propose its local updates, which is persisted in log for later recovery. These local updates later get committed and applied to the mapping table. However, the commits happen sequentially based on timestamps. This gave us a chance to reconcile any possible conflict. We're going to discuss this later in the index rewrite page. Page mapping table is persisted regularly by writing a snapshot into external stream. This is a procedure we call that page mapping checkpoint. This greatly reduces the recovery time, as we only need to replay updates with greater timestamps from the log. Now we'll discuss a few important page mapping operations. Checkpoint, the user data checkpoint, happens when memory buffer size reaches a threshold. For each key value pair, we have to find the corresponding data page in the file table. Then the data belonging to the same data page will be grouped as a delta page and written together. This then proposes appending this delta page ID in the mapping table. This is apparently more compute intensive than memory buffer checkpointing in conventional SM tree, as each key value pair requires a tree traversal, but it only modifies the mappings of data pages. The tree structure is not touched, so it's quite simple to run those checkpoints concurrently. When the delta length reaches a threshold, the page is compacted. Depending on the size of the delta pages, the compaction may exclude the base page to avoid excessive write amplification. This is referred to consolidation. In this case, delta 1 and 2 are rewritten and replace the mapping chain by the new page. Note that it's possible when the compaction happened, delta 3 is still not there, so the compaction will not be able to see it. If the ratio of the total size of delta pages and the base page reaches a threshold, all the pages, including the base page, will be rewritten. This is referred to overwrite, but for page mapping, it's the same as consolidation, except there's a flag saying the base page is no longer needed during the read operation. After the compaction, the original mappings delta 1 and delta 2 are still kept for a while for the snapshot query with old timestamp. When no such transaction exists, those entries will be reclaimed. It's quite possible an overwrite compaction generates more than one delta page. So while we do allow a page mapping includes multiple pages, this could affect the read performance and increase memory usage. So when the page count reaches a threshold, we like to propagate the updates to the parent index. For example, in this case, page P with its deltas are rewritten to 3 pages, QRS. We append a delta mapping to its parent index to point to these pages directly. Now, this is the interesting part. We mentioned earlier that page mapping operations, they can happen concurrently. So there might be another checkpoint that tries to append a delta to P. When it commits, page P no longer exists. We solve this conflict by just temporarily remember the rewrite the P to QRS, so the delta 5 in this figure will be linked correctly to QR and S. The second part we want to talk about today is the garbage collection. While append-only file system brings us so many benefits, for example, like very easy to support the snapshot isolation, it does come at a price. The old, obsolete data require garbage collection so the resources can be released. For example, when delta 1 and 2 are merged into new pages, the original mapping are kept for existing readers. This is called in-memory garbage object. And it is managed by the committing window. When no reader with smaller timestamp exists, this garbage object will be reclaimed. Stream garbage, however, is more complicated. They are generated from compaction, where data are rewritten into new pages. This renders some pages useless. We'd like to remove those extents with very high garbage ratio. A naive solution is just to fully scan the index of our tree, which gives us a view of all valid pages that are still in use. Then we calculate the extent garbage ratio to decide which extent need garbage collection. Pages that still have references, they need to be rewritten so the extent becomes empty and can be reclaimed. Of course, in practice, we have much more complicated algorithms to reduce the tracking cost. It can be found in our research paper. ArkDB is also designed to support scale-out. It has built-in support for data partitioning, in particular, fast partition split and merge operations. Although these operations are usually from the service layer, but under some situations, for example, too many requests, too much data, we'd like to split the database into multiple child partitions. Fast partition split is critical to achieve high availability, as it involves steps during which the store is not available. The data in our design involve two parts. those in the memory buffer, they can be recovered by just replaying the write-ahead log with the proper key range. For those in the file table, we would like to take just a slice of the tree that belongs to the result key range as fast as possible. Because our underlying stream is implemented on top of distributed file system, we don't have to rewrite the whole tree, but only those pages on the split boundary you can see in this figure. And those page mappings can also be compacted along with the split. To verify the performance of our system, we conducted the experiments in 2 environments, depending on the file system and the threading implementations. Those are the hardware configurations. I won't just go into too much detail here. The first slide shows the throughput curve for the ingest-only workload on our local server after 100 million uniform distributed key value updates. ArkDB's average throughput is about twice of RocksDB. But please keep in mind, this is not a direct comparison because ArkDB uses user-level cooperative multitasking for better CPU utilization. For fairness, we just gave RocksDB enough threads to reach its maximum performance. Here, the write amplification, though, of ArkDB is 3.1. That's about 1/3 of the RocksDB is about 9.5. Because of this significant write amplification reduction from this localized compaction approach, ArkDB also offers better performance consistency. The second slide shows the memory footprint of page mapping table, along with ingestion of 100 million uniformly distributed key values on a pre-populated B+ tree, also with 100 million key values. The memory usage quickly climbs up and then enters the steady state with fluctuations, around 10 megabytes. The delta change threshold in this case for page compaction is 4, and the count of pages with the mapping entries stay around 150,000-160,000, while the total page count reaches 500,000. This result actually shows the ArkDB is able to shrink the page mapping table when it's necessary. The last slide shows the throughput is doubled after a 32 gig partition gets split into 16 gig child partitions, served by 2 different nodes, of course. During the pre-split stage, incoming traffic keep being served, though the writes will need to be replayed upon the child partition startup. There is a brief period of service unavailability during this replay stage. That's because the incoming write traffic is very heavy. Transaction data build up in the user transaction log. In our case, the replay actually takes a few seconds to complete. We are still working on several areas to reduce this service downtime. For example, we can do a parallel replay. Currently, the several storage services are already modified to adapt to the new design, but this is a big change, so it's still under production testing. We also need to provide enough data recovery and backup tools because data safety is always our primary concern in public cloud. Finally, for existing data in L7 tree, we need to figure out a simple way for the migration. This work has been accepted by SIGMOD 2021, and this is the title of our paper. You can find more details that we don't have enough time to talk today. So yeah, thank you. Thank you for listening.